Hi there, it's Chem Coach Powers, and we are about to take a journey into Avogadro's law. And the ideal gas law. Okay, we're going to talk about some really cool concepts about gas today. One of my favorite things that I've ever seen, I think, is going to be on this lecture. I'm going to show you a picture of it, and I just love it, and it makes my brain go, what? So hopefully you like it. So we're going to talk about how to solve problems using gas stoichiometry at STP. In other words, you can solve gas problems with stoichiometry. We've been showing you some laws, and these laws are great, but there are some problems that you can solve without the law, perhaps. At a particular standard temperature and pressure, you can use another value I'm going to give you today, and you don't have to use one of those laws as long as you're at STP. And then we're going to show you how to solve problems using the ideal gas law, and that's going to jump us into the lab that we're going to be doing soon as well, because we're going to do a lab on the ideal gas law. So your criteria for success today: given a volume of gas in a chemical reaction, you will be able to use the standard molar volume, and that's something you'll memorize, to find the moles of gas at STP, and vice versa. If I give you the moles of gas, you can figure out standard molar volume, that kind of stuff. All right, and I can use the mole ratio to determine the volume of any other gas involved in the reaction. So we're going to learn about how gases, when they're all, when you have a chemical reaction and they're all gases, that you can use as coefficients as the molar ratio. Given 3 of the 4 gas variables, I can use the ideal gas law to calculate the unknown quantity. The ideal gas law is a pretty fun little formula that you can use for ideal gases which don't even exist. All right, so let's talk about Gay-Lussac's law of combining volumes. Now, if you look at hydrogen and oxygen coming together, they make water vapor. Now, if we were looking at their volumes, we would be like, oh, 2 liters plus 1 liter gives us, and we can't do the normal math here. We can't say that it gives us 3 liters, all right? What we have to say is that 2 liters and 1 liter of these gases are going to give us 2 liters of water. Now, notice that that's the same as the coefficient, okay? Now, these are all gases, and so this is true of gases. This is what Gay-Lussac had discovered. He said, you know what? These gases are interacting with each other in whole number ratios, just like the balanced chemical equation does, right? Just like the number of moles do. And that's kind of important because that gave him this idea about how gases were behaving very much like the moles were behaving. And so maybe the gases had a relationship to the number of moles. And that's where we come up with Avogadro's law here in a second. All right, so another example, hydrogen gas and chlorine gas gives you hydrochloric acid as a gas. In this case, again, 1 plus 1 does equal 2, but that's not the important part. The part that's important is noticing that the 1 and the 1 and the 2 are just like the balanced chemical equation, right? The coefficients of the chemical equation. So when you compare those balanced equations with the expressions, you notice that the volumes of the gases are the same as the coefficients, right? That the ratios are the same. And that's what Gay-Lussac's law of combining volumes says. Volumes of gaseous reactants and products can be expressed as ratios of small whole numbers. Now, remember, we learned about something like this, when we were learning about the law of definite proportions, right? And this is kind of the same thing. Gases helped us understand that initial idea when we first came up with it. Now, Avogadro's law is something that is just mind-blowing to me, all right? Amadeo Avogadro basically looked at this law of combining volumes of gases, and he could see that it did not violate the idea that Dalton had that there were indivisible atoms, okay? He was able to say, you know what, gas molecules could contain more than one atom. It could be diatomic, for instance, right? And this is one of the things that helped them to understand that some of these gases and some other compounds were actually diatomic or might have been a little bit more involved and might have had a few different elements in it. And so he came up with this idea today that we know of as Avogadro's law, which says that equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. Now, this is kind of bizarre. This is a box that is 22.4 liters of volume in size, okay? So you've seen a 2-liter bottle, right? Well, basically, we can get 11 2-liter bottles in this space. You're like, there's no way you're getting 11, maybe 4 powers, right? I know, right? But here's the thing. Those 2-liter bottles, they waste a ton of space. That's why they got all those curves on them and stuff. They can sell you something that looks big, but it's really not carrying nearly as much volume as a square would, all right, or cube, I should say. So what Avogadro figured out was that at standard temperature and pressure, if you have a mole of gas, it's going to fill up 22.4 liters, okay? That is what we call the standard molar volume. No matter what gas, whether it had oxygen, which might be heavier than helium, right, or hydrogen, it doesn't matter if they're heavier and they might be more dense per se, they're going to take up the same amount of space. Now, when I say more dense, if they're taking up 22.4 liters and they all have exactly the same number of particles, that means that this one's going to have more mass in the same amount of space, right? And if you have more mass in the same amount of space, and then you have something that's more dense. But that's kind of wild. Gases are so spread out, they're so moving all over the place and all spread out that you can have the same same volume and same number of particles, but you'd have a different mass of that gas. And you guys have seen that, right? I mean, it makes sense. If you think about helium balloons versus the balloons that you blow up, if you had the same amount of air put into both of those, if they were both under atmospheric pressure, then the helium balloon would float. Why? Because it's less dense, because its particles have less mass, and so it's able to float. But those things have the same amount of particles in them. It's 6.022 times 10 to the 23rd. This is where we get Avogadro's number, right? That space, that 22.4 liters, is going to be 1 mole. 6.022 times 10 to the 23rd. It's on there somewhere too, right? Somewhere. Yeah. Of course, they have 6.023, which, you know, whatever. It's 6.022 according to our book. I don't know what that one is. All right. So this is indicating that gas volume is directly proportional to the amount of gas at a given temperature and pressure. Okay. The volume is proportional to the amount of gas, the number of particles. Now, the equation basically is that volume is proportional to particles, okay? So that's a direct proportionality. Now, this one is going to blow your mind, all right? Still blows my mind. Aluminum foil. This is true. You take sulfur hexafluoride. Now, it's pretty big, right? 146.06 compared to what we were just looking at there with 32 of oxygen. Huge, 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 huge molecule. This is sulfur 6 fluorines, SF6, okay? So this has got 146.606 AMU. Big, big, big thing. But if you fill up a container with sulfur hexafluoride, you could actually float aluminum foil on it. Make a little aluminum foil boat and you stick it in there and it's going to float. It's pretty amazing. Now, what you're seeing here in this picture is they've taken, you know, some of the vapor that comes off of dry ice and they've poured it in the top. So they actually have 2 different gases here. They've got the gas, which is the sulfur hexafluoride, which is the clear stuff. And then they've got some of the carbon dioxide vapor, right? So it's actually water vapor. So they've got some water vapor sitting up on top of that. And, you know, we have to start asking ourselves a little bit about some of the properties of gases here, right? And I put this question at the bottom because this is the question that blows my mind. Can different densities of gas have the same number of particles in the same space and still have this effect? Is it really true that sulfur hexafluoride actually has the exact same number of particles in that amount of space as helium would? Well, I don't know the answer to that. I know that Avogadro would say yes, but I have some doubts. And, you know, maybe someday you can go get your chemistry PhD and come back and tell me what the truth of the matter is here. But you do have to think about a couple things, which are important to look at here. So you have some variables. So if I have a bigger gas particle, but it's at the same temperature, that means that those gas particles are actually moving around at a different speed, right? Bigger particles, you got to think about kinetic energy. The formula for kinetic energy, in case you don't remember, 1/2 mv squared, right? So if my mass is bigger, then my velocity has got to be slower if I have the same kinetic energy. Average kinetic energy is temperature, right? So I've got to have these particles in this sulfur hexafluoride are actually moving around slower than the particles of helium would be, for instance, okay? And it's also true that you got to imagine that the pressure is going to be caused not by the same number of collisions. You're going to have fewer collisions with this sulfur hexafluoride. Why? Because those collisions, the sulfur hexafluoride is big, and so it's going to be making a bigger impact every time it hits. So if you want to have the same pressure, you have fewer collisions. Okay, so both of those things are things that you could, reason out. But the thing that I can't reason out is, would it really have the same number of particles? Are there really 6.022 times 10 to the 23rd particles under that pressure and temperature of that gas compared to others? Now look at this gas. Now we've talked about gases, and gases are defined as being able to take the shape and the volume of the container. That sulfur hexafluoride is definitely not taking the volume of that container, is it? It's stuck. It's so dense, it's sticking down inside. So is it really defined as a gas according to what Avogadro did in his studies? I don't know. Like I say, I'm not like an advanced scientist that has done these studies in a chemical laboratory, but I have done some math. And when I've done the math and I've looked at the density of sulfur hexafluoride, and I go through and I take all the numbers and I work my way through the number I came up with, and I could be completely wrong here. And I don't mind being wrong, but I sure like the discovery of trying to figure stuff out. 6.036 times 10 to the 23rd particles. In that particular amount of space, and like the 22.4 liters. Yeah, it does, maybe there is not the same amount. I don't know. Well, anyway, you figure it out if you want to. It's fun to explore. So that's our molar volume of gas. All right. Still cool one way or the other. So remember that you're going to remember that this is true for an ideal gas. Okay. Now, again, is sulfur hexafluoride considered an ideal gas? You're right. Does it have completely elastic collisions? Does it not have any attraction to the particles? These particles are pretty big. Maybe they're actually starting to get a little bit attracted to each other, right? Like that water vapor that's sitting at the top too. Like, that's not really an ideal gas either, because it would be spreading out, right away. And it's not. It's cold enough that it's kind of sticking together on top of that sulfur hexafluoride. Is it behaving as an ideal gas right there? No, I don't think so. So, sulfur hexafluoride might just not be an ideal gas. And so maybe that's why it isn't really going to meet Avogadro's law. I don't know. You tell me. So according to Avogadro's law, 1 mole of any ideal gas will occupy the same volume as 1 mole of any other ideal gas at the same conditions, despite mass differences. Again, there's no such thing as an ideal gas. Okay. Yes, we get that. Gases are approaching ideal conditions when they are at high temperatures, right? And when they are at low pressures. Okay, so in other words, they can spread out, and then you have an ideal gas. And so in those conditions, STP. But of course, STP isn't exactly those conditions of high temperatures and low pressures, right? And yet Avogadro found that to be true at STP. So volume in which 1 mole of an ideal gas will maintain 101.325 kilopascals, or 1 atmosphere of pressure, at 273.15 Kelvin, which is known as standard temperature, is known as the standard molar volume of gas, and that volume is 22.41410 liters, rounded to 22.4 liters. What this means for you is that you can do stoichiometry problems. You're like, Power, stop rambling. What are you talking about? This is not helping me. Well, I know, but it's so cool. I just can't help but ramble. Okay, so what is this going to help you with? This is going to help you with doing stoichiometry problems in gases. Okay, what are you talking about? I'm talking about mole to volume conversions. If I have a gas, then I can say there are 22.4 liters of that gas in 1 mole of that gas. Okay, so I can have a little problem like this, right? I can basically use that as a conversion factor. And so here I'm given 5 liters of gas. Well, can I tell you how many moles I have? Yes, if it is at STP. Now, again, super important here. You've got to have it at STP. If it's not at STP, this is not true. You're going to have to use the ideal gas law, right? So if it's at STP, then you can do this little formula. You can do this little conversion factor, and you can get your answers of moles, all right? Here's another example on this one, right? You can say 0.768 moles of a gas is equal to 17.2 liters of a gas at STP. Can't do it if it's not at STP, all right? So this is great. I now have a new conversion factor, and you better memorize that one. Okay, 1 mole of any gas is equal to 22.4 liters of gas at STP. Memorize that. You're going to use that. So let's see if you can do it. We're going to do a little practice, right? What volume does 0.0685 moles of an ideal gas occupy at STP? And B, what quantity of an ideal gas in moles is contained in 2.21 liters at STP? So why don't you do a little pause and practice, and we'll see how you do. We'll come back and see what you get. Ready? And pause. You're back. Yay, I missed you. All right, so here's what you should have come up with. You start with your given. You use that molar volume, right? That standard molar volume. And moles cancel. Now, what gas is it? It doesn't really matter as long as it's a gas, right? But this could have been, let's say, O2 But we'd have to have O2 here, right? We'd have to have O2 here. Like whatever gas we're dealing with, let's make sure that we have that gas in all those same places. In this case, they haven't told you. We're just saying it's the same gas. So you get 1.53 liters of that gas is your answer for the first one. For the second one, now we're starting with the liters. And notice how our conversion factors have swapped, right? Over here, we had 22.4 on top, and here we had 22.4 on bottom. Again, what is going on there? Well, nothing weird, right? We're just making sure that what's on bottom cancels out with what's on top, right? So if it's liters, then we better make sure the liters is on bottom. If there's moles, then we better make sure the moles is on bottom. But make sure you always have that number of 22.4 with the liters, right? 22.4 liters. That's the space. All right, so make sure you have that. It's not 22.4 moles. It's 22.4 liters. Make sure you get those connected correctly. All right, so let's go into some more stoichiometry. Because equal volumes of ideal gases at the same temperature and pressure contain equal number of particles. That's called Avogadro's law, right? Then for the gaseous reactants and products, the coefficients in the chemical reactions are going to be equal to the volume ratio. So we can now just assume volume values and just use those as ratios if I have a balanced chemical reaction with gaseous reactants and products, okay? So again, we have to assume the conditions are constant, so we're not changing the temperature and pressure, we're keeping them constant. So now we can do these volume to volume equations. We can say the volume of our given in liters is going to, I can use a unit equality to do volume of my unknown in liters. So all I have to do, this is stoichiometry, right? Start off every stoichiometry problem with a balanced chemical equation. So I start with my balanced chemical equation and I say, what am I starting at and where am I going, right? In this case, I can use these conversion factors of volume to volume as I'm trying to move through my equation. All right, and that's just one of the many steps that you could have, right? Is just volume to volume comparison. Then you set up your problem, you calculate, you're good. All right, so let's see what this kind of a problem looks like. This kind of a problem looks like this. Xenon gas reacts with fluorine gas to produce xenon hexafluoride. If a researcher needs 3.14 liters of xenon hexafluoride for an experiment, what volume of fluorine will she need to begin with? Okay, well, let's see. What have we been given, right? Remember we said we want to go from one thing to the next. We got to have a balanced chemical reaction. Oh my goodness, we got to do also start with the balanced chemical equation, right? That's our first thing. So xenon plus fluorine gas gives me xenon hexafluoride. Because I've got 6 of the fluorines here, then I'm going to have a 3 coefficient popping in front of my F2. You didn't forget to do F2, right? Because that's a diatomic gas, right? It's one of our Brinkelhoff gases. Now I've got my balanced equation. Now, if these are all gases, right? Xenon gas, put a little G there if we want, fluorine gas, xenon hexafluoride. If these are all gases, then I can use these values, the coefficients, as the molar ratios, right? I mean, it's obviously molar ratio, but I can use the volume ratio. So I can just start straight with 3.14 liters, and I want to go to my fluorine, and so I can create a conversion factor of 1 to 3 with liters because I have a 1 to 3 conversion factor already. And so this makes this problem easy and quick and simple. And so it looks like this. 3.14 liters of xenon hexafluoride, and my conversion factor is 3 liters of fluorine for every 1 liter of xenon hexafluoride. And then I get my answer of 9.42 liters of fluorine. All right, so easy, easy, easy peasy. I didn't have to go to grams and calculate all that crazy stuff. As long as they're all in gases, then the molar ratio are equal to my gaseous volume ratios. And I can just, if I'm just going from volume to volume, whoo, super easy. All right, your turn. Okay, you get to try this one, see how you do. One method used in the 18th century to produce hydrogen was to pass steam through red-hot steel tubes to achieve the following reaction. You've got 3 irons plus 4 waters gives me some iron. Ooh, this is an iron 4 oxide. Oh, wow. Well, what in the world is this actually? What iron is this? We've got 2 charge. Let's just figure this out real quick. 2 negative, so I've got 8. Here, oh, this is one of the more crazies. How do I take 3 times what equals 8? So this is actually, I think it's like iron, black iron oxide or something. It actually is shifting from a 2+ charge to a 3+ charge in different situations. And so it actually ends up with this overall charge that's somewhere between 2 and 3, right? Because you can see if I multiplied this, if this was a +2, I'd end up having a +6. And if this was a +3, I'd end up having a +9, right? And so this iron with a 3 after it has got to be something right in between a 3 and a 2. And so this is like a coordinate. This might be called a coordinated covalent. No, not no, never mind. Ignore that. I didn't say that. But it actually has more than one charge. All right, it fluctuates between a 3 and a 2 charge because of the coordination. We're just going to call it that. Anyway, that is totally off track. Start solving your problem and ignore me. +4 of our hydrogens. Now notice again what we have. Okay, this one is a gas and this one is a gas. So if I'm doing a relationship between iron and this Fe3O4, I cannot use that concept, right? The concept that we just talked about about gases and molar volumes. But if I'm talking about my relationship between water and hydrogen, then I can use these coefficients, and it is something I can do. So anyway, I'm giving you too many clues and I'm giving you too many distractors. Ignore all that cool stuff up there. And why don't you go ahead and pause it and practice to see what you get. And Japan, yay! All right, so 500 liters of steam react. What volume of hydrogen gas? So here's our steam, and the hydrogen gas will be formed. Oh, pretty easy, right? Because I've got a 4-to-4 ratio, which is like a 1-to-1 ratio. Ah, man, power's just making me show my work. Okay, fine, I'll show my work. So I've got to do 500 liters. Like, I can do it in my head, Powers. I know. I could even do this one in my head, and I'm not as smart as you are. So 500 liters, and now I want to go to, where's my, there it is, steam, H2O, okay, as a gas. I don't have to put the G there. And so now I can just say 4 liters of H2O is going to be equal to 4 liters of H2. Oh my goodness, it's so easy. So I get my answer. I had to show my work though, didn't I? And what about this 4? Do I have to, use that as my sig figs? No, those are ratios. You don't have to use those as sig figs. That's a unit conversion factor. It's a 4-to-4. It's an exact number. And so I can just say, hey, my answer is 500 point, same number as sig figs, right, of the hydrogen gas. And boom, done. Oh my goodness, it's so easy. All right, they're not always going to be that easy, but you're just going to use those ratios, right? It's not bad at all. Let's see if you can do another one. If all volume measurements are made at the same temperature and pressure, what volume of hydrogen gas is needed to react completely with 4.55 liters of oxygen gas to produce water vapor? I know you can do it. I believe in you. Pause and practice. Ching! Welcome back. So glad to see you. Let's see what our given is. Well, we've got to start all our stoichiometry problems with a what? What? We've got to start with a balanced chemical equation, right? So what volume of hydrogen gas is needed to react completely with oxygen gas to give us water vapor? All right, well, we've done these before. We can know how to balance those, right? It's a 2-1, 2 reactant in this case. And so if I start with 4.55 liters of O2, and I want to see how much hydrogen is needed to react completely with that, then I've got to use my oxygen on bottom. Where's my oxygen? Oh, there it is. 1 liter of oxygen. And then I'm going to hydrogen, so I've got to do 2 liters of hydrogen on top. And so I'm just going to take 4.55 times 2, and we'll get 9.10. Yep. I'm old. You can use a calculator. You can't. Okay, you can. 9.1. How many sig figs? We should have 3 sig figs because we started with 3 sig figs. Liters of hydrogen gas, right? Man, he's saying hard. This is easy. Yeah. All we got to do is make sure our units are on bottom that cancel with the units on top, and that we understand this concept of the molar volume with our balanced chemical reaction. Boom. Oh, there it is. All right. So Let's do another problem here. Mass volume calculations are also possible. Oh my goodness, there are so many possibilities. How many liters of hydrogen gas at STP can be produced by the reaction of 4.60 grams of sodium and excess water according to the following equation? Yay, they give us the equation. 2Na plus 2H2O gives us H2 plus 2NaOH. All right, we're rocking it, man. They're giving us all sorts of stuff. All we got to do is the hard work. Oh, don't look at that answer. All right, let's just talk about the plan before I show you. Okay, so we've got the formula. And now, again, we're just showing you how we can do mass and volume calculations. We've been given grams, all right, of sodium. We don't have to do any limiting reactant because we have excess water, so we're fine. We know that sodium is the one we got to start with. And then it says how many liters of hydrogen. Oh, yay, STP. STP is huge because as soon as I see STP, that means I can use that what number? 22.4. Yay! It's an easy number to go with. All right, so here's where we start. Now, you've got to go from the grams to moles, right? We still got to go to moles. Why? Because once we're in moles, we can go from moles of one substance to moles of the other substance, right? From sodium to hydrogen. But once we're there in hydrogen and now we have a gas, right? It's still our hydrogen, then we can use that 22.4 because we're at STP. Only use that if you're at what? STP powers. Yeah, that's right. STP, P for powers. So then I get my answer, 2.24 liters. Whoa, are you ready? Are you ready? Okay, back up. Oh, wait, you can pause it anyway. You don't need to look at it again. Don't forget, though, we are missing something here. Liters of hydrogen gas. Oh, you're so good. I'm so proud of you. All right, let's look at the next one. Your turn this time. You get to practice it, and we're going to see if you come up with the right answer. And I believe in you. You've got excess bromine reacting with 5.60 liters of hydrogen to produce what mass of hydrogen bromide at STP? Oh, okay, this is a little different than the last one, right? Don't be jumping into doing a gram conversion. We're not starting with grams this time. It's giving us a little bit of a shortcut. We're starting with 5.60 liters. So we don't have to go from the grams to the moles and then moles to gas in this case. We can just go straight to our gas, all right? Now, one of the things that we have to ask ourselves, again, is whether or not these are all gases. And we're going to go ahead, since they haven't told us, we're going to go ahead and tell you yes. Let's call them all gases, okay? All right, pause and practice. Boom, let's go. And welcome back. Here's your work. This is what you would show. You'd start with that liters. We can, again, this is at STP, right? Oh my goodness, did you check to see if it was at STP? You did? Yay! Because at STP, it just makes our problem so much easier. Because then we can use that 22.4, right? So we can go from our liters of hydrogen and we can go immediately from liters to moles, right? It's a moles to liters road. And so then we can go from moles to moles, boom, boom. And they wanted to know number of grams. So now we have to use our grams at the end here instead of at the beginning, right? So we've got grams of HBr for every mole of HBr. And oh my goodness, this person is not showing their work all the way. They get to show their final values. 40.5 grams of HBr. Did you get it? You did because you're a rock star. All right, now let's go on to ideal gases. Remember, ideal gases don't exist, so let's just pretend. Here's some moments of pretend. Remember, ideal gases are those gases that have perfectly elastic collisions, right? They don't get attracted to each other at all. Just pretend that's hypothetical gas. We use these formulas. Just remember, we use these ideal gas formulas because a lot of gases come very close to ideal gases. Very little attraction between each other, right? And so we can just approximate the answer. And the approximate answer, if we use this ideal gas law, it's actually an approximate answer. But that approximate answer is really close. And I know you say that close is only good in horseshoes and hand grenades. You've heard of that? Like, whoo, that was close. You ever played horseshoes? My grandpa was a pro horseshoe player. Actually, both of my grandpas were, from both my mom and my dad's side. And I know I'm distracting you, but this is wild, right? Like I found out that they both were like professional Colorado, like horseshoe players. And I don't know if they ever played each other or if they ever knew each other even before this. As far as I know, they didn't, but they were both like amazing horseshoe players. Anyway, why does that matter? Because when you get close, the horseshoe, if you're with just one horseshoe away, you still get a point, right? You just got to get it close to the stake, and it's also important in hand grenades because you don't want to die. Ooh, that's a close call. Yeah, but this also important in ideal gases. It's close enough. Ideal gases. It's close enough. All right. I know some of you are really annoyed right now, and some of you are actually smiling. All right. Real gases act like ideal gases under certain conditions. What conditions are they again? High temperatures, low pressures. And so we can take this gas law, PV equals nRT. Okay, this is pressure, volume, the number of moles, and the temperature, and something R. And this R is a constant that you would normally either have to memorize or be given, right? It's a constant. And basically the way that they come up with this R value is by looking at all the other variables under STP, right? So if I wanted to resolve this problem for R, I would take and I would have PV over NT. And so when I come up with the number that R is equal to, this 0.0821 liter atmospheres per mole Kelvin, that's basically taking the pressure, 1 atmosphere, the volume, 22.4 liters, the number of moles, all right, and it's 1 mole, sorry, 1 mole, and then the temperature, and of course we do this in Kelvin, very good, and so we're at 290, no, 0 degrees, I can't remember if it's 298, no, not 298, 290, me, I can't remember if it's at 0 degrees, which is 273, or if it's at 20 degrees, which is 293. I don't know. Figure it out. Math. I'm going to math this. Totally mathing this to death. 3.15. No. It's 22.4 divided by 273.15. Yeah, this is the 273. It's at 0 degrees Celsius. I know I probably have that in the previous slide, but you know, it's just important to double check, and it's fun to math it. So 273.15, that you take those numbers together, and of course this is the 22.4, and you could have it longer, and it's going to give you that 0.0821. Now there's another one that you're going to see sometimes, and that is the 8.315, and that just, the only difference there is that they throw in the 101.325 kilopascals for that value instead of atmospheres. Anyway, R is the gas constant, okay? And the units are super important in this. Notice how we have liter atmospheres per mole Kelvin, and it's very important. I had liter atmospheres per mole Kelvin. Why? Because if I were doing it and I were to do it with the kilopascals, it would be 8.315 liter kilopascals per mole Kelvin, right? And so make sure you have the right units, because you're actually going to have to look to see what units you have to know what value you're supposed to use, whether you're supposed to use the 0.0821 or the 8.315. Okay, so look for that kilopascals or the atmospheres. It makes a difference. All right, so again, ideal gas, hypothetical concept. It's a model. No gas follows the ideal gas law, but they get close. And so again, these gases are close at low pressures and high temperatures. And again, it's the best thing you can do is to think about it as the behavior approached by a real gas under certain conditions. And that's why we use these laws, okay? So ideal gas, all spread out, high temperatures, low pressures, move around really fast. Real gas, yeah, probably lower temperatures and higher pressures, a lot more collisions. You might actually have some attractions, right? You might have some attractions in these spaces. Yeah, and that is a real gas, okay? All right. Let's look at an example. What's the pressure in atmospheres exerted by 0.500 mole sample of nitrogen gas in a 10-liter container at 290 K? Do I need to have the balanced chemical equation? No. This is just a formula, okay? This is another one of those formula problems, just like our other gas laws. So I just got to punch out the values, right? 0.500 moles, that's N. And 10 liters, that's V. 298K, that's T, all right? So I just got to plug those in, and I got to look, what were my values in? My values for pressure. Well, I'm solving for pressure, so I can choose either value of R, but I've only really told you the one. So you choose that value of R, and your answer is going to be in atmospheres, right? So again, you got to look at your R value to see what your answer is going to be in. So looking at that value might help you choose which R value to use, or seeing the R value will choose and tell you which unit you're going to have. So your answer is going to be in atmospheres. Why? Because you have that in atmospheres, right? So my final answer is 1.22 atmospheres. That's how you do these problems. Real simple. Just plug it in, right? Plug it in, baby. Oh my goodness, it's your turn? Sweet. We must be getting close to the end of this lecture, which I know you are excited about. So let's get going. Try this one on your own and we'll see how you do. Tank of hydrogen gas has a volume of 22.9 liters, holds 14.0 moles of the gas at 12 degrees Celsius. Celsius. Ooh, we don't like that. We must change that. What is the reading on the pressure gauge in atmospheres? Atmospheres. Oh, that's the pressure we're looking for, which means we can use that 0.08 to 1. R value. You ready? Pause it and boop. You're back. Let's see what we get. All right, we plug it all in. We had 14 moles. Again, we want to follow the full gems here. You're not seeing the full gems being shown. We should be showing our givens first, right? So let's do it just so you make sure you know what you should also have. So volume equals 22.9 liters. The moles equals 14.0 moles, right? The temperature is equal to 12.0 degrees Celsius, which means we're going to convert that into 285.2 Kelvin. Do you have to put down the R value? You should, because you want to make sure that you're looking for atmospheres. You have the right one. 0.0821 liter atmospheres per mole Kelvin. Boom. All right. Now you're ready to do it. 1, 2, 3, 4. Solving for P. P question mark. Number of atmospheres. Yay! All right. Then we get our answer. 14.3 atmospheres. How many sig figs can we have? Well, we had 3, 3, 3. Yep. Well, actually, when we did our temperature, we ended up having 4 with that. So we're good. 3 is the number we should have. Boom. Done. I told you we were close to doing the lecture, getting it finished, and here we are. Our objectives review. Can we solve problems using gas stoichiometry at STP? Yes, now we can use that 22.4 liters per mole. We know how to use that. And we can also use this whole thing where we go liters to liters as long as they're both gases, right, in a balanced chemical equation. Boom, boom. Can we solve problems using the ideal gas law? PV equals nRT. Boom. Nert. I don't know. I'm a little weird. It's okay. It's much better to have me on video because in real life situation with you guys in class, I'm way too serious. So it's much more fun to have me like this. Trust me. Can you figure out criteria for success? Review. Given a volume of gas in a chemical reaction, can you use the standard molar volume to find the moles of gas at SCP? Standard volume, what is that again? Oh, 22.4 liters per mole. Yeah, Powers, I can do that. All right, and you can use the mole ratio to determine volume of any other gas involved in the reaction. 4 moles of this to 4 moles of that. Why? Oh, yeah, 4 liters of that, 4 liters of that. They're both gases. Given 3 of the 4 gas variables, I can use the ideal gas law to calculate the unknown quantity. Yes, indeed, PV equals nRT, but you can solve for P, you can solve for N. For T, you can solve for them all. Boom, done. Okay, thanks. I hope you enjoyed it. I love this stuff. I love that, especially Avogadro's law, mind-blowing, tinfoil on sulfur hexafluoride. This long lecture was worth it just to see that and think about that for a while, right? All right. God bless you guys. You have an awesome day. And be kind to one another. Why? Because being kind is the way to be. Have a good day.